Hello, so I missed a young man who came by for my office hours. I am not in room 473 in physics. That's my office, and that's where you can find me, but to go to my office hours from 9 to 11 in the morning, that's in room 201 in Koffler. So that's downstairs, and I'm there with all of the other TAs. You can always go there if you want help. But I thought I would take the occasion to just talk about what you guys need to do for this particular lab. So in this lab, you have a material something that's in a vial, that depending on what temperature it is, sometimes it's going to be pink, and then other times it's going to show up as blue. So how can you control that? Well, in a chemical reaction, if you have blue stuff, and it can change, or it can chemically react and turn into red stuff, then what you've been talking about in lecture is the kinds of energetic concerns that determine whether the reaction is product favored, which means that you have more blue stuff, or whether the reaction is reactant favored, which means that you have red stuff. And the point of this thermochemical material is that if you change the temperature, you can change the equilibrium point from you have more red stuff to you have more blue stuff. In other words, you can make it appear blue at particular temperatures and appear more red at other temperatures. So what we're going to do is we're going to have two vials, and we're going to put 20 milliliters each of the blue stuff. $20 milliliters of the pink stuff, and we are going to put different ratios of each one of those solutions into a single 5 milliliter vial. Okay, with what purpose? We want to find the point where the switch over from being product favored to being reactant favored happens somewhere in the temperature that we can control. So let's say that at room temperature, the red stuff is favored. Then it should be that we can put the vial on ice, and that will shift the equilibrium so that the blue stuff is favored, and that means that the vial turns blue. You are going to try at least 7 different ratios of the blue material and the pink material mixed into a 5 milliliter vial. So what would one way of doing that be? Well, you could put 4 milliliters of the blue material and 1 milliliter of the pink material, and that would add up to 5. So you're looking for 7 different combinations of these two materials that add up to 5 milliliters. What is your goal? Your goal is to find a point where this vial that contains both of the solutions changes from blue to pink when you put it on ice, or from pink to blue when you put it on ice. In other words, it's sensitive within the temperatures that you have control of. And that's pretty much all that we're doing in this particular lab. So I just wanted to talk about what this has to do with what your lecture is about. I'm going to draw a Peck diagram. And I would just like to remind you that on a Peck diagram, the potential energy goes up and down. The zero of the potential energy is up here, which means that the further down, the further negative you get in potential energy, the more negative potential energy you have, the stronger the force is between those bonds, and therefore the stronger the bond is. And then left and right on this thing is the number of configurations. Another word for this is up and down. The vertical axis is called the enthalpy, and another word for the left and right axis is called the entropy. The way that I remember which one is which is that I always remember how graphite turns into diamond. So if I'm graphite, graphite being the form of carbon that is in your pencil, and I want to turn into a diamond, what happens there? First off, is that likely to happen? Do we have a lot of diamonds sitting around, or do we have a lot of graphite sitting around? Obviously, we have a whole lot of graphite, and that's reflected in the fact that this is both energetically favored, that is, you can go to a lower potential energy state by turning from graphite into diamond, and it is also configurationally favored. So you're going from the top left to the bottom right, that's favored in both this direction and this direction, so this is definitely going to happen. If you let diamond sit around, it does eventually evaporate on its own into graphite. So diamond has a half-life. It's a very long half-life, but it does evaporate. How would I turn graphite into diamond? I would need to do two things. To get from graphite up to diamond, that's not favored, so I would have to increase the temperature. Increasing the temperature would allow you to access less negative potential energy states. In other words, if you're wiggling around with a lot of potential energy, there's a possibility of forming a bond using that energy. And then how would you go this direction? So in other words, how do we change the number of configurations? Well, if I went from a system that had a lot of configurations to something that had fewer configurations, I'm confining that system. So I can go from graphite to diamond by increasing the pressure. So the pressure is an external variable that you have to manipulate the number of configurations, and the temperature is an external configuration, an external variable that you can have to access lower potential energy states. In other words, if you want to go from graphite to diamond, the kind of places that happens is like in volcanoes, it's in meteor craters, it's places where there was very high temperature and very high pressure that allowed the graphite to convert into diamond. So let's see what that means about the reaction that we're talking about. We're talking about going from blue stuff into red stuff. So we're not really sure what the Peck diagram for this thing looks like. But let's suppose it looks something like this. If it did look like this, then you would be configurationally advantaged to go this way. So in terms of the number of configurations, the system wants to change from blue to red, but it can't because it has to gain enough energy to make up that change in potential energy. So how would you get from blue to red? In other words, how would you convert more of this thing into this thing? Well, you could do it by increasing the temperature. Okay, so in other words, our experiment, this project, is all about having a vial that has a combination of blue and red that's constantly interacting. The blue is turning into red, the red is turning into blue. And you can manipulate how much of the reaction stays in blue, or in other words, whether the equilibrium is more towards blue, or whether it's more product-related favored, or whether it's more reactant favored, whether it's more red. You can manipulate where the equilibrium occurs by changing the temperature. We are not going to change the temperature this experiment. I just wanted to talk for you a little bit because there was a good bit of confusion about first the Beer's law, and then also just the notion of what what we were doing, how we were manipulating the color of the material, and I wanted to go over that. Beer's law will not be necessary for this lab, and we will talk about it at the beginning when I see you this week. So you will not use Beer's law this week for the preparatory work. What are you doing? All you are doing this week is telling me that you are going to pour different ratios of these two materials into a 5 milliliter vial with the objective of finding at least 2 combinations that will change color when you put them on ice. Okay, and that, I think, was everything that I wanted to talk about. If you have any other questions, then you can shoot me an email. I just wanted to really quickly cover the K constant because we're covering it in lab before you do in class. So what is a K constant? A K constant is something that characterizes whether a reaction is product favored or reactant favored. If it's neutral, if it's neither product nor reactant favored, then the K constant is equal to 1. The K constant is a ratio of the probability that reactants will collide in just such a way that they break up and are able to recombine, and divided by the probability that the products collide. And like I say, this is a ratio, so when the probability that the reactants collide is equal to the probability that the products collide, then this is equal to 1. So what is a probability that that multiple things are going to happen? If you were to roll a dice, the probability of getting a 1 on that dice would be the number of ways that you can get 1, which is one way to get a 1, divided by the total number of outcomes, which is 6. So the probability of rolling a 1 on a dice is 1/6. The probability of rolling 2 ones would it be 1/6 plus 1/6 or 1/6 times 1/6? It turns out it's 1/6 times 1/6. Or 1/6 squared. This is the way that probabilities combine anytime you have what's called independent events. In other words, independence that the first dice, this one, does not influence the outcome of the second dice. So the probability that the reactants are going to collide follows this multiplicative rule. And it's going to be the concentration of each one of my products, the concentration of this thing, times the concentration, because the concentration is telling you how many moles you have in a particular liter, and that's going to characterize how likely that they are going to collide with each other. And then it's not plus 4 times this concentration, it's this concentration raised to the 4th power, because probabilities are multiplicative, not additive. So the final expression for the K constant is the concentration, I'm just going to call it the concentration of the first thing. I'll label this, say, 1 for the first thing, 2 for the second thing, 3 for the third thing, and 4 for the fourth thing. So this is a reaction where 2 things react and form 2 other things. So it's the concentration of the first thing raised to however many, the stoichiometric constant out in front, which in this case is 1, so there's 1 of these kinds of molecules that's required, times the concentration of this thing raised to the 4th power, because all 4 of those molecules have to run into each other at the same time in order to collide in just exactly the right way. The second concentration raised to the 4th power divided by the third thing times the 4th thing raised to its stoichiometric coefficient, which is 2, raised to the 2nd power. What does this quantity K tell you? Well, if you were to graph K, if K was 1, that means that it is neither product favored nor reactant, so this is neutral. If K is greater than 1, that means that this quantity here, the numerator is larger than the denominator. Well, the numerator was that the products are the reactants. So the numerator was the reactants. So if K is more than 1, that means that the reactants, the concentrations on the top, are greater, the probability of the reactants colliding is greater than the probability of the products colliding is greater than the probability of the reactants colliding. So if K is greater than 1, in other words, if you're up here somewhere, that means that you are product favored. If K is less than 1, somewhere down here, that means that you are reactant favored. And you can change, K is in fact a function of temperature. So you can change from something being product favored, in other words blue, to something being reactant favored, in other words pink, depending on what temperature it is. And this particular lab is all about how you can change a reaction from being product favored to reactant favored. In any event, I hope that was useful. Thanks, Adam. Bye.